Hello, and welcome to the Falcon review of Costanzo's physiology textbook. My name is Patrick Sosnay, and I'm going to be talking with you about respiratory physiology. In this first section, we're going to talk about the structure of the respiratory system, and specifically how the structure facilitates function, both to get the air in and out of the lungs and to efficiently exchange gas. What the respiratory system has to do is pretty simple. It's got to get oxygen into the body, and it's got to get carbon dioxide out of the body. With each inspiratory and expiratory cycle, we bring fresh air into the lungs. Fresh air that gets down to the alveoli allows for oxygen and carbon dioxide gas exchange between the alveoli, where the gas is, and the capillary, where the blood is. Then that air is exhaled. I think about the respiratory system kind of like a tree. You've got the trunk of the tree and the branches of the tree. Those are kind of like the conducting airways. And then you've got the leaves of the tree. Those are kind of like the alveoli. We can break the respiratory system down into the conducting zone, which just gets air in and out of the lungs, and the respiratory zone, actually where the gas exchange occurs, like the leaves. Figure 5.1, which is on page 184 in your text, goes through an example of the distinctions between the conducting zone and the respiratory zone. The conducting zone, or upper airways, includes the nose, the nasopharynx, the larynx, trachea, bronchi, bronchioles, all the way down to terminal bronchioles. These structures serve to get the air in and out, obviously, but more importantly to warm and humidify the air, and also they play a key role acting as a filter to remove particulate matter or viruses or bacteria that you might inhale that potentially would be harmful to the respiratory system. The trachea, or the trunk of our tree, is the main conducting airway, which divides into two main stem bronchi to each of the lungs. The bronchi go on to divide about between 18 and 25 more times, depending on where you're going in the lungs. Here in the textbook, they say there are 23 divisions. These conducting or upper airway cells are lined with mucus-producing cells, and the respiratory epithelium, have cilia or hair follicles on them that help to trap and remove inhaled particles. The big particles are usually filtered out in the nose, but small particles make it down lower in the lung. There, they're captured by mucus, swept up by the mucociliary elevator, and able to be coughed out. You can tell you're in the conducting zone if you see on a histology section that there's smooth muscle around the airway. The smooth muscle has sympathetic and parasympathetic intervention. Those two act in a yin and a yang fashion, opposing each other to control the airway diameter. When we stimulate the sympathetic adrenal neurons, we do so through the beta-2 receptor. Stimulating that causes relaxation of the bronchial smooth muscle, dilation of the airways, bronchodilation. This is important because we pharmacologically manipulate this by activating the beta-2 receptors with beta agonists such as isoproterenol or albuterol that you might be familiar with if you have asthma. The parasympathetic nervous system works on the airway via muscarinic receptors. When you stimulate the muscarinic receptors, we get contraction, constriction of the airways, bronchoconstriction. I'm going to plant the idea in your head now. Why would you want to make your airways smaller? Once again, Figure 5.1 reviews the differences in function and histology between the conducting zone and the respiratory zone. When we change the diameter of the airway, we change the resistance of airflow through that airway. Therefore, the autonomic nervous system has an effect on airway diameter, which is going to have predictable effects on airway resistance and on airflow. We can control how much air gets in and out of our lungs by our autonomic nervous system. When we give beta-adrenergic agonists such as epinephrine, isoproterenol, or commonly inhaled albuterol, we dilate the airways. We use this as a treatment for asthma. Now let's get down to the respiratory zone, or what I call the business end of the lung. The respiratory zone is anywhere in the lungs where you've got structures, airways that are lined with alveoli, or the air sacs. We're going to see change in the histology from the pseudostratified columnar epithelium down to squamous epithelium of the respiratory zones, where the alveoli are facilitating gas exchange. Specifically, the alveoli are off of the respiratory bronchioles, the alveolar ducts, and the individual alveolar sacs. The respiratory bronchioles, to some extent, represent the transition between the conducting airway and the respiratory zone. Like the conducting airway, there's some cilia there, there's some smooth muscle there, but there's gas exchange going on because alveoli occasionally butt off their walls. All of these distinctions are somewhat arbitrary. If you look at a pathology sample and you see alveoli, then you know you're in the respiratory zone. If you look and don't see alveoli, you can assume you're in the conducting zone. Things that would support that as well would be seeing ciliated cells or seeing smooth muscle surrounding the airways. The alveolar ducts are completely lined with alveoli. There are no cilia and very, very little smooth muscle. The alveolar ducts then terminate in the alveolar sacs, which are also lined with alveoli. This entire alveolar system serves to create a large surface area to facilitate gas exchange. The alveoli themselves are these pouch-like evaginations off of the walls of the respiratory zone. Each lung has got about 300 million of them, and the diameter of an individual alveoli, Costanza estimates at 200 microns. In the respiratory zone is where we've got the exchange of oxygen coming out of the alveoli into the bloodstream and carbon dioxide going the other way. The large surface area for gas exchange facilitates this diffusion. We can see elastic fibers lining the alveolar walls. The individual epithelial cells of the alveoli are called pneumocytes. They are both type 1 and type 2 pneumocytes. Those type 2 pneumocytes serve an important role. They synthesize surfactant. Surfactant is necessary to reduce surface tension in the individual alveoli. These type 2 pneumocytes also probably represent the regenerative capacity for the alveoli. Within the alveoli, you may see phagocytic cells called alveolar macrophages. These are just like macrophages you'd see in other tissues. The alveolar macrophages are going to serve a last line of defense. Any particle of dust, debris, or pathogen that makes it down the alveoli should be scavenged by the alveolar macrophages. Once they fill with debris, they'll migrate proximally up to the bronchioles. There, the beating cilia can cough them up to the upper airway where they can be swallowed or expectorated. The pulmonary blood flow, which is outlined in Chapter 4, Figure 4.1, is a dual circulation. The pulmonary blood flow is the entire cardiac output from the right heart. The pulmonary arteries branch into smaller arteries and travel with the bronchi towards the respiratory zones. The smallest arteries then divide into arterioles and branch into our extensive capillary network, which surround the alveoli. There are regional differences in capillary blood flow within the lung. We're going to spend a lot of time talking about that. When somebody's standing up, blood flow is least at the apex, or the top of the lung, and it's highest at the base. You can think about this as gravity pulling down on the blood. But if someone's supine, they're lying down, these gravitational effects are going to disappear, or the blood is going to pool dependent. As in all of our organs, the regulation of blood flow is controlled by altering the resistance of the pulmonary arterioles. Change in the pulmonary arterial resistance are controlled by numerous factors, and these factors are different in the lung than they are in the peripheral tissue. We're going to talk about that more. In addition to the pulmonary blood flow coming off the pulmonary artery out of the right heart, we also have a bronchial circulation. This is blood supply to those large conducting airways, which are not participating in gas exchange. It's a small fraction of the total pulmonary blood flow. It's important to remember that the bronchial circulation comes off the aorta as opposed to the pulmonic circulation coming from the right heart. Bronchial circulation is often a culprit when someone has hemoptysis or is coughing up blood. That concludes our first section talking about structure and how it relates to function. We're going to continue talking about lung volumes in the next section.